right, we're going to talk about integrals as accumulating functions and functions of net change. And the biggest application that we have for accumulating and net change is distance traveled, whether it's net or total distance traveled. And as we'll see, there are other things that we can accumulate besides distance. And I'm actually going to do a problem that is involving in a tropical island and the number of mosquitoes on an island. So that should be an interesting problem to do together. So having said that, let's do a quick review of the fundamental theorem of calculus. And the fundamental theorem of calculus, I'm going to specifically start with part 2, which is the evaluation piece. So the fundamental theorem of calculus part 2 states that if we have an integral from a to b of some function f of x dx, that's going to equal the antiderivative, capital F, evaluated at b minus the antiderivative evaluated at a. Okay? Now I'm going to rearrange this and I'm going to solve for f of b by moving f of a to the other side of the equation. So we're going to say f of b here is equal to the integral from a to b of f of x dx plus the antiderivative evaluated at a. Okay? And now let's make f a function of t and make it an area accumulation function. So let's say that big capital F of t then is equal to the integral from a to t of f of x dx plus f of a. Now I have two versions here. One is in terms of x only, and one is an area accumulation function based on where we're stopping for time, or t. Well, I would like you to consider that this right here would be an initial condition. For example, where you happen to be if you're a particle at time equals a. And if a is 0, that would be your initial position before you started moving. And I'd like you to consider this part of the fundamental theorem of calculus, your net change. So what happens is you have an initial condition, and then you add some area under the curve, which is your net change, and that gives you your final position. So we could create an area accumulation function that is position. And we could call it x of t and state that that's going to be the integral from some time a to some time t of your velocity of x dx. Now we have to have a dummy variable here because our varying is the upper limit of integration, not the function itself in here, plus x of a, okay? And this is a position function where you are at time t. Where x of a is an initial position given. Okay? Now, this could be a position function or another kind of function, which we'll talk about later. And remembering that this is the initial condition. And this was all generated from the fundamental theorem of calculus part 2, which is the evaluation piece. All right, now, how is that important? Well, we need to discuss the difference between net distance and total distance traveled. Okay, well, net distance is a fancy way of saying displacement, which is a word that's used in physics a lot. It's displacement. And it doesn't take into account how far you went one direction or how far you went into another direction, like total distance traveled does. Displacement is just the difference between where you started and where you stopped. So that I would say is delta x. Well, I would suggest to you that delta x could be written as x of t minus x of a if I started at a and ended at t, which could be the integral from 0 to t of v of x dx. So this could be displacement here because this is delta x. And where did we get that from? Well, I just added or subtracted the x of a over to the other side and got the displacement. So I could say, this is the displacement, that x of t, my position, again, I'm referring to my position function, is equal to the integral from, I should put an a here, a to t of v of x dx plus where I started. So this right here would be displacement plus the initial position. Oops, I can't spell initial. Okay, and so how do you get displacement? You just subtract your final position from your initial position and you get the net displacement, okay? Now, there are other representations for net distance or displacement. Sometimes you can have representations. Other representations besides we've got delta x, you can have delta s or delta y. Those are other displacement notations, but it's still the same right here. Okay, now what's the difference between displacement and total distance traveled? Well, total distance traveled takes the distance that you walk to the right and the distance you walk to the left and adds them together. It takes the absolute value of the distance that you walked to the left because that's negative in our calculus world. And so we force it to be positive so we know how far we actually walked. It's like when you're taking a walk or something and you want your mileage, just because you walked right, 2 miles and left a mile doesn't mean you walked 1 mile. You actually walked 3. So total distance traveled does have some applications. Okay, so let's talk about what total distance traveled is. And let's say we're going to start at time 1 and go to time 2. That's our interval. Well, that's going to equal the integral from time 1 to time 2 of the absolute value of your velocity function, dt. And I hope that makes sense to everybody because the absolute value function, when you apply it to velocity, forces all the area that the velocity might have under the curve to be above the curve, and then you can add them together, and you have all positive numbers when you add them together. I'm going to do an example here in just a second where when we do the total distance traveled, we are not going to be using the absolute value function, but we're going to take the negative area and subtract an integral, which forces it positive, okay? All right, so in your notes, I put a summary page here for particle motion, and I call it a reference guide. And it talks about all the notation for position, velocity, acceleration, when we're at the origin, just all sorts of information. And just a reminder that average velocity is equal to the change in position over the change in time, which is the displacement over time. The average velocity can also be the integral because average velocity could be the average value of the velocity function. So you could do 1 over b minus a times the integral from a to b of v of t dt. So, and same thing is true for average acceleration, all right? And things that we already know from differential calculus, the velocity of the particle is positive, then we know the particle is moving right, or it might be moving up. If the velocity of the particle is negative, then it's moving to the left or down. If the acceleration is positive, then the velocity is increasing because velocity's derivative is acceleration. If the acceleration is negative, then the velocity is decreasing. And speed is the magnitude of the velocity. So that's an important thing to know, magnitude. It is directionless. It has no sign, SIGN. Okay? If the velocity and the acceleration have the same sign, both positive or both negative, then the speed is increasing, or your particle is speeding up because the acceleration and the velocity are working together. If the velocity and the acceleration are the opposite sign, where one's positive and the other one's negative, then the speed is decreasing, or your particle is slowing down because the velocity and the acceleration are working against each other. Think about when you throw a ball in the air. When you throw a ball up in the air initially, it's slowing down because the acceleration due to gravity is negative, and you've given it positive velocity, and they are working to get not opposed to each other, so the ball is slowing down until it reaches the pinnacle, and then once it gets to the pinnacle, it starts falling back to the ground, and when it's falling back to the ground, the velocity and the acceleration are both negative, so the ball is speeding up. Okay? So to determine the distance traveled over a time interval, you calculate the sum of the absolute values of the differences in position, so the net displacements, and you add them together. Okay? And I just went over how you find the final position and everything. All right, so let's do some examples. I think that's important. All right, so I got this from your book, and the first one is, let's say we're given the velocity as 6 sine of 3t, and we're told it's between 0 and pi over 2. We're supposed to use analytic methods to determine when the particle is moving to the right, to the left, and stopped, which requires us to do a sign chart. Okay, so in order to do a sign chart, here we go. Here's my sign chart, and I know I'm going from 0 to pi over 2. Oops. And now, in order to do a sign chart for the velocity, I got to find the zeros. So 6 sine of 3t. Well, sine is going to be 0 when 3t is equal to 0, and when 3t is equal to pi, and when 3t is equal to 2 pi, and we'll see if that's far enough. So the first time will be when t is 0, so I'll put a 0 above here, and then the next time will be when t is pi over 3, and then when t is equal to 2 pi over 3, which happens to be outside the zone here from 0 to pi over 2. So I'm going to put pi over 3 right here and put a 0. And what we know about the sine curve is the sine starts on the midline, and the midline for 6 sine of 3t happens to be 0. So there's my midline. And sine starts on the midline, which makes sense because I found the 0 here. Okay, now sine starts and goes up in amplitude and then goes to its 0. So here it goes. We're going to go to the 0, and then we're going to come down here. And let's make it a different color so you can see it. All right, so we know my sine curve is positive, and then we know it's negative. All right, so for part A, it states, determine when the particle is moving to the right. Well, a particle is going to be moving to the right when the velocity is positive. So we can say particle moves right, or moving right, from 0 to pi over 3, since our justification is v of t is greater than 0. We can say the particle is moving left from pi over 3 to pi over 2, since v of t is less than 0, and the particle is stopped at t equals 0 and pi over 3, since v of t is equal to 0 at those locations, right? That's not too bad. Part B, find the particle's displacement for the given time interval. Okay, so displacement means I don't have to take into account, the how far it went right and how far it went left. So I can say the displacement from 0 to pi over 2 is equal to the integral from 0 to pi over 2 of 6 sine of 3t dt. Now I can factor out a 6, and I get the integral from 0 to pi over 2 of sine of 3t dt. The antiderivative of sine of 3t is, I believe, negative cosine 3t over 3 from 0 to pi over 2. Now, when you find the antiderivative of a cosine function with a linear composition here, meaning I have a line in here, when we were taking the derivative of cosine a long time ago, what did we do with the derivative of the inside? Well, we multiplied. So when you're going backwards, instead of multiplying, you divide. Okay? So when you divide, you're going to get negative 3 cosine t over 3. All right, now we're going to plug in pi over 2. So we get 6 times negative cosine of 3 pi over 2, which happens to be 0. Okay, minus the cosine, of 0. The cosine of 0 is 1. So this will be minus 1. Let's try again. 1/3. Cosine of 0 is 1. So this is a minus of minus 1/3. Equals positive 2 units. Right? So my displacement is 2 units. So that's the answer to part B. And then it also asks us, if the initial position is 3, what's the particle's final position? Okay, well, I can say that the particle's final position pi over 2 is going to equal the integral from 0 to pi over 2 of 6 sine 3t dt plus my original position, which is x of 0, which, or I should say s. They've got us as s here, so we'll make this s. Right, because they've determined our position function is going to be s. So s of 0, which they're telling us is 3. So remembering that this is the displacement, and this is the initial position, I can say that at s of pi over 2, I'm equal to 2 plus 3, or 5. So s of pi over 2 is equal to 5. So that's my final position. Okay, so part C says, find the total distance traveled by the particle. Well, do I have any part of the distance from 0 to pi over 2 that's negative? Well, I do, and it's from negative pi over, or it's from pi over 3 to pi over 2. So what do we have to do? All right, well, we have to say the total distance traveled. Hopefully I have enough space. From 0 to pi over 2 is going to be the addition of two integrals. So it's going to be the integral from 0 to pi over 3 of 6 sine of 3t dt minus the integral from pi over 2 to pi over 3 of 6 sine 3t dt. Now, why did I subtract this portion here? Well, because it's negative area, and if I subtract a negative number, that makes it positive. Okay, so I already know the antiderivative of this function because I did it here. So I can say, I can even reduce this. I can say this is negative 2 cosine of 3t evaluated between 0 and pi over 3 minus negative 2 cosine 3t evaluated between pi over 2 and pi over, I'm sorry, I got it backwards. You guys sat there and watched me write that backwards, right? It's early. All right, so this is pi over 2 up here, I'm sorry, and this is pi over 3 down here. Pi over 3 to pi over 2. Worried about the space. All right, so here we go. This is negative 2 times, well, I'm going to put the pi over 3 in here, and that's the cosine of pi. Cosine of pi is negative 1 minus the cosine of 0, which is 1. Okay, so that turns out to be negative 2 times negative 2, which is a positive 4, which I totally expected because this is a positive area here. All right, minus, well, what happens when I plug in pi over 2 here? I get, we're going to do this whole thing here, negative 2 times, when I plug pi over 2 in here, I get the cosine of 3 pi over 2, which is 0, minus the cosine of pi, which is minus 1. All right, so this is minus a negative 2 times 1, which is negative 2. And then minus a minus makes it a plus 2, makes it a 6. So 6 units is my total distance traveled. Okay. All right, I know that's a tight squeeze in here, and I'll prove it to you with the calculator. So how do we do this on the calculator? Okay, so I'm going to do the total distance traveled. Well, that's going to be the integral, which is f3 second integrate, 6 times the second sine of 3t, close the parentheses, comma t, comma, 0, comma, second pi divided by 3. And that's going to give us 4, which we expected. And now we're going to go from second pi divided by 3 to pi over 2. And you'll see that that's negative 2. But when I force it positive, it's a positive 6. Now, I can also take this and do the absolute value here so that we can see that it's the absolute value. So I want to put absolute value in here. So I'm going to type in alpha A, alpha B, alpha S, parentheses. That gives me the absolute value function. And I close the absolute value. And if I do that, I will get a whopping. Oh, it helps if I change that to pi over 2. Wouldn't it help if I changed it to pi over 2? Yeah, because if 4 is, only to pi over 3. There we go. We get 6. All right. So we know when it's moving right when the velocity is greater than 0. We know when it's moving left when the velocity is less than 0. We know the particle is stopped when the velocity is 0. The displacement is nothing more than the integral from 0 to pi over 2, because this is delta S. And we got, we did the antiderivative and got 2 units was our displacement. And then to find where your final position is, you take your displacement, which is the integral, and you add it to the initial position. Now, this is a powerful statement here. So when you're writing out your answer, you should, write S of pi over 2 equals the integral displacement, right, plus the initial position. And then the total distance traveled. How did we tackle that problem? Well, we took the positive area, split it out in an integral all by itself, and then subtracted the negative area, because when you subtract a negative, it forces it positive. And if we were going to do it on the calculator, you can actually use absolute value bars to do your displacement. All right, let's do another one. All right, this one here is not a trig function, because I know you love trig functions so much. That's why I started off with them. This is number 8. And so we're going to do the same exact problem where part A said, determine when the particle is moving to the right and left and stopped. So I'm going to do a sign chart. And my sign chart is going to go from 0 to 3. And I have a closed interval. So I'm putting my closed interval there on my sign chart. And this is V of t. Now I need to know when this velocity is 0. Well, this velocity is 0 when the numerator is 0, which is at t equals 0. And it's undefined when the velocity here is undefined when the denominator is 0. So 1 plus t squared is never 0. Let's think about that, right? 1 plus t squared equal to 0. T squared equals, I'm writing it up here, negative 1. That doesn't happen in the real world. So this derivative is never undefined. And the denominator is a parabola that is always positive. So I know that this parabola is always positive for the denominator. And the numerator is a line. A line with what kind of slope? A positive slope with a 0 at 0. So there are our two functions that we superimpose. And so my sign chart says, guess what? We're positive the whole way, which is really nice. So part A, when it asks us, when is the particle moving right? Particle is moving right from 0 to 3, since v of t is greater than 0. Particle is moving left. Now, as I have spoken about in the past, open and closed brackets on moving left and right are fine for the AP folks. I just like to use open and closed open intervals for that. So anyway, moving left, never, since v of t is not less than 0. Now that's the sign for is not, like not equals. So we can say never negative. That also works. Okay, particle is stopped. At t equals 0, since v of t equals 0. So those are our three things for part A. Part B asked to find the particle's displacement for the given time interval. So the displacement from 0 to 3 is equal to the integral from 0 to 3 of t over 1 plus t squared dt. And now we have to use a certain method here to integrate this, and it's integration by u substitution. We were going to let u equal the denominator 1 plus t squared, du equals 2t dt, du over 2 is equal to t dt. And so I can say that my integral is going to be 1/2, and then I'm going to let this be 1 over u du, because I took care of this part is 1/2 du, and that's u in the denominator. So this turns out to be 1/2 natural log of the absolute value of u. So I can bring it back and say this is equal to 1/2 the natural log of the absolute value. What is u? 1 plus t squared, evaluated between 0 and 3. So we get 1/2 times the natural log of, when I plug 3 in here, I get 10, because it's 1 plus 9, minus the natural log of 1, which is equal to 1/2 natural log of 10, because the natural log of 1 is 0. So that's our displacement, which is, delta S is 1/2 natural log of 10. Now, part B also asks, what's our final position? Well, our initial position they gave us was 3, so our final position at 3 is going to equal the integral from 0 to 3 of t over 1 plus t squared dt, plus my initial position. Now I know that this right here is, again, the displacement, and this right here is the initial position. Which they gave us as s of 0 is 3. So this is going to be 1/2 the natural log of 10 plus 3. And this is my final position mark, or my position at 3. All right, now part C asks for the total distance traveled. Now I like to do this problem because this was a gift in disguise. Okay, the total distance traveled here. Do I have any negative area under the velocity curve? The answer is no, I don't. So in this case, the total distance traveled is equal to the displacement. So the total distance traveled is equal to the integral from 0 to 3. And you could put absolute value bars here if you want, but you don't have to because this integral is always positive. So we know that this is 1/2 natural log of 10, right? Because since v of t is always greater than 0, from 0 to 3, displacement is equal to the velocity. Is equal to total distance traveled. And you say thank you very much and go on to the next problem. All right, I also wanted to do a couple of AP examples so that you can see that actually, the free response questions, you're definitely going to get integrals as net change or accumulation. Okay, so the first one I like to do is from 2012 because this kind of models what we did in the first question, which was the sixth sine of 3t. So in this question, and this is a non-calculator question, because it's question number 6. It says for the interval of t between 0 and 12, a particle moves along the x-axis. The velocity of the particle at time t is given by the velocity equals cosine of pi over 6 times t. The particle is at position x equals -2 at time t equals 0. So right here, they're giving us a point in time, and they're saying that x of 0 is equal to -2. So they're giving us an initial condition. So we need to keep that in the back of our mind. Okay, so part A says for t between 0 and 12, when is the particle moving to the left? All right, so now we got to get to work here. So the velocity is equal to the cosine of pi over 6 times t. And I need to know when it's moving to the left. So I need to do a sign chart from 0 to 12. Okay, now cosine is 0 when its angle argument, when pi over 6, t is equal to pi over 2, because the cosine of pi over 2 is equal to 0. So when I multiply both sides by 6 over pi, I get 3. And then it's also 0, so I can put a 3 on here. When pi over 6, t will equal 3 pi over 2, which is the other quadrantal angle. So t is going to equal, if I multiply both sides by 6 over pi, I get 18 over 2, which is 9. And then I always go one more just to check. So this is going to be pi over 6t equals 5 pi over 2. If I multiply both sides by 6 over pi, I get 30. I get 30 over 2, which is 15. And guess what? That's not in the zone here, so I don't have to worry about it. And now I'm going to superimpose the cosine graph. Well, the cosine starts off the midline and up in amplitude. So my midline in this equation here is at 0, which is nice. And so I start up in amplitude, pass through my 0, come back up, and then pass through my 0 again. Okay, so this is going to be plus, minus, plus for my sign chart. And I can say for part A then, particle moving left from 3 to 9, since v of t is less than 0. So part A is done. Yay. That's probably worth 2 points. All right, part B says write but do not evaluate an integral expression that gives the total distance traveled by the particle from 0 to 6. Now 6 is not the entire distance here, so 6 goes to about here. All right, but I notice that I have some positive velocity and some negative velocity, and they're asking for total distance traveled. So I can say total distance traveled from 0 to 6 is going to equal, I'm going to combine two integrals here. All right, I'm going to say the integral from 0 to 3 of v of t dt. Now I don't have to rewrite what v of t is because they've defined it up here. Minus the integral from 3 to 6. Now why did I subtract? Because I knew the area under the curve here is negative. So subtracting a negative area makes it positive, and I can say that is my expression for total distance traveled from 0 to 6. Okay, so that's part B. Part C says find the acceleration of the particle at time t. Okay, so acceleration is the derivative of velocity, which in this case, if I take the derivative of this cosine function, the derivative of cosine is negative sine pi over 6 t times pi over 6. So this is going to be negative pi over 6 sine of pi over 6 t. So I'm sure that's worth a point. And then it continues to ask, is the speed of the particle increasing or decreasing, or neither at t equal 4? So we need to know what a of 4 is. Well, a of 4 is going to be negative pi over 6 times the sine. When I plug 4 in here, I get 2 pi over 3, which is equal to negative pi over 6 times the sine of pi over 3, which is root 2 pi over 3, I'm sorry, is root 3 over 2. So this is negative pi root 3 over 12. I don't know what that is, but it's a negative number. And now I need to find the velocity at 4. All right, so the velocity is cosine of pi over 6 times 4, which is 2 pi over 3. Now the cosine of 2 pi over 3, this is a second quadrant angle here, 2 pi over 3, so this is negative 1/2. Both of these numbers are negative. So what does that say about the speed? Well, we know the speed is increasing. At t equal 4, since v of t and a of t have the same sign. The speed increasing is another way of saying speeding up. Okay, and you must compare the signs, SIGNs, of the velocity and the acceleration to see if they're working together or if they're working against each other. Okay, that's something common that a lot of AP folks miss, and I don't want you guys to fall in that boat. Okay, so that's part C. I'm sure you would get a point for the acceleration function, a point for these two values, and a point for your statement as to whether it's increasing and decreasing with a reason, because it says explain the reasoning. All right, part D says find the position of the particle at time equal 4. Okay, well, the position of the particle at t equals 4 is going to be x of 4 equals the integral from 0 to 4 of cosine of pi over 6 t dt plus its initial condition, right? Which means I have to, they're not saying just write an integral, I have to actually integrate this, okay? So, and I know that this is a negative 2 because that was my initial condition they gave us in the problem. Okay, so I have to find the antiderivative of this. I'm running out of space here, but that's going to be antiderivative of cosine is a positive sign. The pi over 6 t. Now I have to divide by this pi over 6, which is the same as multiplying by 6 over pi. right? Such that we're going from 0 to 4. And this is going to be minus 2 actually on the outside of this. So let's plug in 4. So we get 6 over pi times, now when I plug in 4, I get the sine of 2 pi over 3, the sine of 2 pi over 3, I'll write it down, minus the sine of 0, minus 2. So let's go up here. All right, 6 over pi times the sine of pi over 3 is root 3 over 2, minus 0, right, which is just 0, minus 2. So we can reduce this to 3 root 3 over pi minus 2. So that's x of 4. Yeah, I think they called it x, so that's good. So this is x of 4 equals that. All right, and so that would be part D. So a particle motion problem isn't really all that difficult if you know, understand the difference between total distance traveled and displacement. I think that's a big deal. All right, let's do another one. This is the one I was talking about earlier, which happens to be the mosquitoes on the tropical island. Now, this is a graphing calculator problem because it's question number 2. So this is a calculator active question. So this problem states for time between 0 and 31, the rate of change of the number of mosquitoes on tropical island at time t days is modeled by R of t, so mosquitoes per day. This is a rate of change of mosquitoes per day. There are 1,000 mosquitoes on tropical island at time t equals 0. So they've given us an initial condition of 0, 1,000 for our mosquitoes. I'm going to call that, M for mosquitoes, right? So part A says, show that the number of mosquitoes is increasing at time t equals 6. Well, okay, so the number of mosquitoes is increasing or decreasing? Well, guess what? I have a rate of change function. So this is the derivative of the number of mosquitoes right here. Okay, so I can say if I know R of t is equal to 5 root t cosine of t over 5. Now this is the number of mosquitoes per day changing, right? So if I know R of 6, which would be 5 root 6 cosine of 6/5, and if we type that in the calculator here, let's see what I have in y equals here. I actually put it in y equals ahead of time. Okay, so that's in y1. So if I go home, I can type y1 parentheses of 6 and diamond approximate, which is 4.438 if I round up. Okay, this is mosquitoes per day. So if the rate of mosquitoes per day is 4.438, that's a positive number, which is greater than 0. So the number of mosquitoes is increasing at t equals 6 days. All right, so part B says, at time t equals 6, the number of mosquitoes is the number of mosquitoes increasing at an increasing rate, or is the number of mosquitoes increasing at a decreasing rate? Give a reason for your answer. So they want to know how this mosquitoes per day number is changing with respect to time. So we need R prime of t. All right, now how do we find R prime of t? Well, where did I put R? I put R in y1. So I'm going to go home and I'm going to go F3 derivative y1 of x, comma x, close. And then there's my derivative right there, right? So I'm going to write that down. That's 5 cosine of x over 5 over 2 root, I should make these t's. Minus root t sine of root t over 5. And I want r prime of 6. Okay, so I'm going to go such that, because I can use the such that bar, x equals 6. And I get negative 1.913. 913 if I'm rounding. Make that 3 more legible there. Okay, so this is mosquitoes per day squared. Now this is a negative number, less than 0. So what does that mean? That means the rate of mosquitoes per day is decreasing. So we will say the number, I'll use the number of mosquitoes is increasing at a decreasing rate. So the mosquitoes per day is decreasing. All right, part C asks for according to the model, how many mosquitoes will be on the island at time t equals 31? That sounds to me like the net number of mosquitoes. So what we're going to do is we're going to say that's the integral from 0 to 31 of r of t dt. And since r of t is defined in the problem, I don't have to rewrite it. But how do we do that on the calculator? Well, wait, they want to know how many mosquitoes were on the island. So we're going to put plus 1,000, right? Because we have this is the net change, right? And this is the initial amount. We call it the initial population of mosquitoes, right? So I have to add 1,000 to it. All right, so I'm going to say F3 integrate y1 of x, because that's where I put it, comma x, comma, we're starting at 0, day 0, going to 31 days, closing that, and we're going to add 1,000, which is my initial condition. Let's see how many mosquitoes we get on the island. What is that? 964. 964.335. But I need to pay attention to the question because it says round your answer to the nearest whole number. Well, the nearest whole number is, so then we would say 964 mosquitoes on island at t equal 31 days. And I might say something like rounded to nearest whole number. All right, part D says, to the nearest whole number, what is the maximum number of mosquitoes from 0 to 31? All right, so maximum number of mosquitoes on a closed interval. So what does that require? I hope all of you all at once said chart, because you would be right. So that means I'm going from 0 to t of r of x dx plus 1,000, because that's the number of mosquitoes. And I know 0's got to go on here, and I know 31's got to go on here. Okay, now at time equals 0, do I know how many mosquitoes are on this island? Well, I know they told me it was 1,000. And the problem was nice because they had us calculate how many were on day 31, and we say 964. Right? So we need to find out if there are any critical points in here where I might have had more mosquitoes. So I need to do a sign chart for R of t between 0 and 31. Okay, so that means I have to graph it. And I put it in here already. That's R. And if I go diamond graph, there it is. Now, I took the liberty of doing this ahead of time so I could save some time on the video. And I made my minimum -1 to 35. Now, why did I put 35? Because the time goes to 31. I just put 35 because I thought that was a good one. And then I just left my x scale as pi over 2 because we're dealing with cosine. And then I only care about the zeros, right, of this function. I only care about the zeros. So I don't care if I see the maxes or mins. So I just went from -10 to 20. Could I have gone from -1 to 1? Sure. Because all I care about are the zeros, right? And whether it's positive or negative. So let's go back to the graph. And so I know it's positive from some number to here. And then I know it's negative here. And then I know it's positive again. So I need these two zeros. And I know that this might be a max and this might be a min. So how do we do that? We go F5, calculate 0. And my lower bound, I'm going to put a 0. And these are any, I don't know, halfway through. Let's put 15. You want, oh, try again. F5, 0, 0. Upper bound. I'm just going to go from the upper bound. And watch my calculator fly. Okay. Nice. Of course it's 0, 0. Let's do it again. F5 one more time. Always while I am on live, I do this the wrong way, right? Here we go. Lower bound, upper bound. What is that? 7.853. 7.854. I'll put. That goes on my chart. 7.854. Okay. Now this is a minimum here. That really doesn't need to go on my charts, but I'm put it on there anyway. F5, 0. I'll do it right this time. And we get 23.562. Okay. Home. Now what do I have to do? I have to evaluate my integral there. So I've already got my integral here, so I'm going to hop up here, grab it, and I'm going to change this to, instead of 31, I'm going to say 7.854 plus 1,000, and we're going to get 1,039 what is that, 3636. And then I'm going to plug in 23.562. Press enter. And what are we going to get? I know this is not going to be the max here because that's a min up here. What is that? 842,405. 842,405. So I know the absolute maximum number of mosquitoes. Can I spell mosquitoes? It's mosquitoes. I like it. I think it's pretty funny. Is 1,039 at t equals 7.854 days, right? And we're going to say rounded to nearest whole number. All right. So we had to check the endpoints on a closed interval here, and that is how you do it. Okay, now I'm going to do one more really quickly, I hope, so we can be done. All right, this next one is a classic problem, and it's the amusement park problem. And this one says the rate at which people enter the amusement park, and this is a calculator question because it's a question too, on a given day is modeled by the function e. So this is I like it, it's e for enter. So they give us this function here. That's the rate people are entering. So that's a derivative, it's a rate of change. People per hour. Okay. And the rate at which people leave the amusement park on the same day is L of t. Well, they gave us this is another rate. This is how the rate they're entering and the rate they're leaving. Both E of t and L of t are measured in people per hour, and time t is measured in hours after midnight. These functions are valid from time between 9 and 23 hours, the hours in which the park is open. At time t equals 9, there are no people in the park. So what is that telling us? Right? So my initial condition is at 9, we have 0. We have 0 people in the park, which makes sense. The park's closed until then. Okay. All right. So part A says, how many people have entered the park by 5 p.m., which is t equals 17? Round your answer to the nearest whole number. Entered the park. So I want to take the integral from 9 to 17 of E of t. Again, since E of t is defined, I don't have to rewrite it because they gave it to us up here. Okay, and that is 15. So let's type it in there. Now I'm going to go up here and I'm going to clear this out. I'm going to put it in my calculator under y1. So I'm going to make a note here. This is going to be under y1 of x. Okay. All right, so that's going to be 15,600 divided by parentheses x to the second minus 24x plus 100. No, wait, plus 160. I'm sorry for the ink, that's not great there. Plus 160. Yep, that looks right. And I'm going to go ahead and put the L in there as well. That's going to be 9890 divided by parentheses x to the second minus 38x plus 370, close. Okay, and I put this in y2 of x just for my memory. Okay, now we're going to integrate. We're going to go home. We'll go back to the home screen and go F3 integrate. No, I just did differentiate. F3 integrate. Where is it? Y1 of x is the entering, comma x, comma 9, comma 17. Close. Enter. Now they gave me this actual number, but I want the approximate. So I'm going to diamond in, enter. And we get, what is that, 6,004 people. Okay, but they want us to round it to the nearest whole number. So about 6,004 people have entered the park at t equals between 9 and 17 hours. Now I want you to think about this. This E of t is people per hour. Okay, and this right here is hours. So what happens when you multiply people per hour times hours, right? Because that's what the units are for this one, and the units are hours here. You get people. Okay, which is pretty cool. All right, part B real quickly says, the price of admission to the park is $15 until 5, and after 5, the price of admission is $11. How many dollars are collected from the admissions? Well, that you would take and multiply the number of people in the park. So we would say admissions dollars, right, are going to equal $15 times the number of people in the park from 9 to 17. That's E of t dt. Plus $11 from 9 to 23. I mean, not 9, but 17 to 23 of E of t dt. And let's plug that in our calculator, right? So I can go back to the front here. I can say 15 times. And then I can say plus 11 times. I'm going to come up and grab this integral here, and I'm going to change it from 9. I'm going to go 17 to 23. Let's see how much money they made. What is that? 104,000 to the nearest whole number, right? $104,048. Okay, earned while the park was open. Part C says, let h of t equal the integral from 0 to t of e of x minus L of x dx from 9 to 23. The value of h of 17 to the nearest number is 3,725. So h of 17 equals 3,725. Well, we'll just analyze this. This h of t is the number of entering minus the number of leaving. So this looks to me like this is, people per hour, right, times hours. So if you take the number of entering minus the number of leaving times how many hours, that to me seems like this h is the number of people in the park, right? Because this is the number who entered and this is the number who left. Okay, find the value of h prime of t. Well, h prime of t is equal to a derivative of an integral, which using the fundamental theorem of calculus is just evaluated this where it stops. So this is e of t minus L of t. So I want to find h prime of 17, which is going to be e of 17 minus L of 17. Now, remembering, where do I have E and L? I have them in Y2 and Y1, right? So I'm just going to go Y1 of 17 minus Y2 of 17. And I'm going to get a number. What is that? Negative 380. Negative 380.281. And then remember, this is people per hour. Okay, so what does this mean? This means that the park is losing people at a rate of 380 people per hour. So at t equals 17, people are leaving park at, do we do it to the nearest whole number? 380.281 people per hour. Okay, now this doesn't say round to the nearest whole person here. Okay, so I didn't say at a negative rate, because if they're leaving at a negative rate, it actually means they're coming into the park, right? So I just said they're leaving the park at 380.281 people per hour because this is a negative number. So leaving is winning. All right, and they want to know what h of 17 is. Well, that's the number of people in the park. At t equals 17 hours. Right? Well, it makes sense because people per hour times hours gives you 17. All right, next. D says, at what time t between 9 and 23, does the model predict the number of people in the park is a maximum? So this is, h of t is the number of people in the park, right? And I have a closed interval again, which means I have to have a chart. So here we go. We're going to do a chart. I'm going to put t, and I'm going to put 9 and 23 on here because I have to. And then I need h of t, and that's going to equal the integral from 0 to t of e of x dx, e of x minus L of x dx, okay? So I need to find out when the derivative is equal to 0. Now remember that this is the derivative here, okay? So I need a sign chart for that. This is h prime. Okay, so I'm going to go diamond y equals, and what's the derivative? Well, it's going to be the top one minus the bottom one. So I can say y1 of x minus y2 of x here. And I'm going to press enter. And I'm going to deselect these because I can go to y4 and say, I don't want to look at that one. And I don't want to look at that one, but I just want to look at this one. And I want to change my window now. I have 35 here. So since I'm going to 23 hours, I'm going to put 25 here. And I only care about the zeros again, so I'm going to leave it like this. Diamond graph. Here we go. So I need to know if this function's ever going to be 0. And it's thinking. So it looks like it's 0 in one location. Now, actually, I'm going to change my window. Let's make the X max to 5,000. Let's see if it's a nicer one to see. Oh, no, 5,000 is too big. Let's make it 2,000, and we'll make this negative 200 so I can see more of the graph. I just want to see a little bit of the graph to see where it crosses. So I go up, the park's increasing in people, and then all of a sudden it starts decreasing. So I need to know what that 0 is, okay? And it's still busy, so I have to wait for it to finish. Okay, so F5, 0, and I'm on this side, then this side. And do you want me to guess? What does that say? 15.795. Okay. So I need to know what the initial people in the park was. Well, I know that that's going to be 0 because they told me it was 0. And then diamond, I want to second quit. I want to go home. And then we're going to take the integral. So F3, the integral from of y3, because that's where I put my function, of x, comma, it's not going to be, this is 9, comma, I'm going to put x alpha c because that was my 0. What is that? 3950. 3950.680. And then we're going to go to 23. Of course, it's the exact answer. I want approximate. It's thinking, it's thinking, it's thinking. One person. One lonely person's left in the park. Okay, and so I'm going from 9 to 23 here. And remember, this is 15.795. And I was positive here and then negative. So I know that's my maximum. So the question's asking, at what time Does the model predict that the number of people in the park is a maximum? So I would say maximum people in park at t equals 15.795 hours. Okay, now my justification is the chart. And why did I have to use a chart? Because I had a closed interval between 9 and 23, and you have to check the endpoints because of the extreme value theorem of calculus, okay? Now, that's all I'm going to do today, mercifully, right? In your notes, you have something called more practice here. These are also AP type problems that I want you to think about. I will do a separate video working these out. Okay, so you guys have a great day, and we will talk with you later. Thanks.